Okay, hi, good evening, everyone. I hope you can hear me. If you can hear me, you can just use some reactions. So, I don't know. All right, thank you. So welcome to our real technical session. And as you all know, we'd have like 1 hour session where we get to learn one or two things. So yes, ground rule before we begin. As usual, we should be respectful to everyone in the session. If you're just asking a question, please mute yourself so that we can minimize background noise and hear what we came here to learn. Engage actively by sharing your thoughts in the chat and dropping your questions. When you are speaking, let it be one person at a time so that we can hear everyone without interruptions, and we kindly use the raise hand function so that we can be orderly. Let's keep the discussions focused on machine learning or the topic on the agenda. We should not spam the chat with irrelevant links or anything that is off topic. Also, feel free to ask a question. We'll have a Q&A session, so please feel free to ask a question, and it's an opportunity for me and you to learn all together. And lastly, let's have fun and enjoy the session and connecting with people. So, I mean, this is the um, agenda that we have. The welcome, then we have the session, and then we have the Q&A and wrap up. So today we're talking about causal inference, an introduction to causal inference, moving beyond correlation. And who is our speaker? Our speaker is Nasiruddin Rahim. He is a data analyst with foundation in statistics, machine learning, and marketing analytics. He has hands-on experience in the world problems, including structural equation modeling and business decisions with causal inference. In fact, this is the first time I'm hearing about causal inference, so I'm very, very interested in this session. He's passionate about data-driven decision making. He actively participates in global data science and communities such as the DSN and AI Focus Group. And I think it's a 9 time hackathon champion. I don't know if those statistics have they've gone up. And his work focuses on bridging the gap between predictive modeling and causal inference, helping organizations move beyond correlation to actionable insights. Nasiruddin is dedicated to teaching and mentoring. You come and mentor me, please. Making complex analytical concepts accessible to diverse audiences. So, with a round of virtual applause, let's welcome Nasiruddin to take this session. It's over to you.
Yes. Good afternoon, everyone. Can you hear me very well?
Yes, I can.
Okay. Yes. Let me share my screen. Can you hear me?
Yes.
Yeah, good afternoon once again, everyone. My name is Nasiruddin Rahim, and I work as a data scientist at Life Science. So whereby we are trying to solve marketing analytics problem with causal inference method and data science method also. So our topic for today is basically a new topic that I'm very sure, as the host said, that this is the first time he's hearing about the topic. So I can also sense it because he said casual. Well, that is normal, but I'm very sure from onset it's going to be causal. So the topic for today is introduction to causal inference, and it simply means we have to move beyond correlation. So our objective for this session is basically 5. So the first thing is that I'm very sure I will make sure that the participants here are able to understand the fundamental differences between correlation and causation. And we are also going to learn about the foundation of causal inference. And we are also going to talk about the engine or the building blocks of causal inference. And we are going to discuss little things about the methodologies. And we are going to see one real-world application. Why thinking causally, it's something that's going to be beneficial to every data scientist. Maybe you are a newbie, you have started applying data science in various organizations you're working at. So these are the main 5 objectives that we have today. So the first section, correlation versus causation. Yes. So what is correlation? I'm very sure that a lot of you, one way or the other, have been able to build 1 or 2 machine learning models. And when we say correlation, it is a statistical measure that we are trying to measure the relationship or association between 2 variables. Now, when you say variables change together, X moves, Y moves, or does F moves and Y is trying to come down, negative correlation, X move up, Y moves up, positive correlations. Then we have the example here, and causation. So understanding the why. So basically, we are trying to talk about that change in A leads to change in B, and it's also required some evidence that, and we have an example for it. So we have 2 scenarios. Imagine that in a particular community, they observe that shark attacks is common, and maybe you as a data scientist, and you find out that, okay, when you check your data, you find out that ice cream consumption or ice cream sales is highly correlated with shark attack. And then, basically what we are trying to do is that we want to solve a particular community problem, right? We want to make a particular intervention. And then they are now saying that ice cream sales are correlated with shark attack. If I may ask, should we ban ice cream? So probably everybody would look like, should we ban ice cream? Okay. Or the second one, maybe you are trying to make a Google search, maybe you come across someone winning a Nobel Prize, and they say, wow, I can also win a Nobel Prize. And then in the long run, you actually find out that, okay, fine, chocolate consumptions and Nobel Prize, they are highly correlated. Then you just feel like, oh, wow, maybe I start eating a lot of chocolates for me to also win Nobel Prizes, right? I'm very sure that mostly everyone is familiar with this word in one way or the other. Maybe you're a data analyst, you're a data scientist, or even sometimes if you are talking randomly with your friends, or maybe you're trying to look at some data point, we all say correlation is not causation. So if you are from statistical background as I am, I think we are going to be very familiar with that particular quote. Correlation is not causation. So, but how do we try to separate them? How do you even know to interpret them? To be honest, over the years in statistical background history, this particular talk have been that the likes of Fishers and some other great researchers have been able to say, but are they able to solve the problem? Then let's move. So the way forward, here comes the man that I really like a lot. His name is Professor Judah Peer. I think from the word is a Jewish Jew there. So he was able to be the pioneer of consulting this modern days. Like when you go on your Google and you find what consulting means, you must see him. And I really love his book on it. Like it is very practical. It also makes a lot of sense. You also understand some historical background that's come from someone that's come from statistics, machine learning, or trying to do causal inference. So that is it. That we have a particular problem, like I said. Should we ban ice cream? Or if you want to win a Nobel Prize, you have to be consuming a lot of chocolate, like you eat chocolate a lot so that you can win Nobel Prize. So the foundation of causal inference, according to Professor Judah, we have 3 ladders of causation. We have 3 main ladders of causation, and from here we can be able to reason behind the difference between correlation is not causation. So if you are able to see that correlation is not causation, then you should be able to understand these 3 ladders very well. The first thing that you have to notice is that the first thing on the ladder is correlation. So we call it association, correlation. The major word is seeing, right? You are trying to do pattern recognition. And I think that is all what we do mostly in machine learning, basic statistics, even in deep learning. You want to recognize the pattern, you just have your X to fit your Y, and you try to observe the accuracy, or even if you want to extend, you do interpretability of your model, right? Then let's move to the second ladder that a lot of us, this is the first time, or let me say some of us have heard about it. I think most of us should have heard about A/B testing or randomized control trials. But maybe few kind of we know what propensities comes or matching methods. So intervention is trying to make it, you are trying to do, like you are trying to intervene. So like I mentioned now, if you are in a community and we see that there is a very high increase in shark attack, and then we are trying to, in our data, we see that we have ice cream to be highly correlated with shark attack. I asked again, okay, fine, are we going to ban ice cream so that shark attack will reduce? So you are trying to make an intervention. And we have the third ladder, which is the third ladder, which is called counterfactuals, right? So we have the word factual, counterfactual. Okay, what if I had done, what if I had done comes after you have done something, right? So can you try to, do you have time machine? So what if I have gone to this place instead of this place, but you have already been somewhere, right? So we also name it, imagine you are trying to imagine a particular stuff. So we can see from the ladder that the first one is like how animals behave or robots behaves, like try to recognize pattern. And second one is a particular child trying to learn his or her environment. When you want to learn, they try to do something. Maybe if I fall down from the chair, I'm going to knock my hand on the floor and stuff like that. And counterfactual, like what if I had, at some point, what if I had made this particular decision? What will have been let me say, something related to opportunity cost, right? So now, I'm very sure a lot of us here have performed some data analysis, let me call it data science pipeline comparison. So when you are trying to do machine learning predictive analytics, we have this, we are going to the business, we define the problem. Okay, we want to do churn prediction. Then from churn prediction, what are the likely features we are going to collect? We are going to collect demographics data, collect the age, you collect some data that relates to socio-economic activities, maybe their income and stuff like that. Then the next thing you do is that you try to find the suitable machine learning models to use, or even deep learning models, and you try to validate the accuracy of your model based on maybe regression, root mean squared error, or you are trying to use a binary classification, you want to use ROC-AUC, and you're trying to, you have your train and test data, you train your model with a particular percentage and test a performance on another percent, it's most times 70, 30, 80, 20. And then the final thing, explainability, feature importance. If I remember vividly, so let me just be a little bit historical here. One of the problems I think we data scientists have mostly is that after we build our model, the business stakeholders do ask, okay, fine, what does this mean? Or what are the features that are important and stuff like that? And then in the recent years, people start coming with, okay, explainability. At some point, some people even say that, okay, using linear regression because, it's highly interpretable, the trade-off is that you don't have that high performance, high accuracy with linear regression, this statistical model, traditional ML model, but it's highly interpretable. You can do, okay, fine, this is our coefficient. You can try to talk that to your stakeholder. But in the early days of when you're trying to use random forest, you are trying to use especially deep learning models, just have your accuracy without interpretability. And then a lot of business, you really need to discuss with the stakeholders. And this is what this is causing, and this is what this is, and this is why, and stuff like that. But basically, all these things still fall under association, trying to do pattern recognition. But when we look at the causal framework, the first thing you are going to define your problem. Then the next thing you are going to do your data generating process, right? We are still going to discuss about that. Then the next thing you are going to identify spurious correlations. Now, when we say correlation is not causation, we are still going to talk about that. You are going to estimate on your data. You are going to validate and explainability, like they mentioned, like you said, yeah, baked in. There's a way that you can explain your model using causal framework, like that everybody in the room, every stakeholder says, okay, this is okay. I think you know what you are doing, and you are doing the right thing at the right time. So after this, then let's look at the main energy of causal inference. We have discussed about causal inference. We have had two set of problems that should we ban ice cream, or for me to win Nobel Prize, I have to start consuming a lot of chocolates. Now, we have three major structures here. This is the building blocks of when you want to move your ladder from association to intervention to even counterfactual. We really have to understand what this means. And if someone is very common with maybe some network analysis that deals with graph in one way or the other, maybe you have seen, okay, fine, you are trying to have an edge. You are trying to have our nodes. Our nodes is basically our features, our variables we have in our data. Why the edge shows the directions. Okay, we can see that, okay, fine. Z causes both X and Y, and we call it the fork. So this is one of the major assumptions, the fork assumption, the fork structure. The next structure is chain, S causes Z, and Z causes what? Z causes Y. And the last one is the collider. The collider is basically that X and Y causes Z. Now, for the fork here, we normally call it confounder. Z is a confounder. For the chain, we call it mediating variable. Z mediates X to Y. And for the collider, is basically X and Y causes what? Causes Z, X and Y give birth to Z, right? So most times I look at this theory structure that fine. The one way or the other, you see differences there, right? And then, like I said, these are the building blocks for causal inference. I hope you can hear me, right? Hello?
Yeah, we can hear you.
All right. So, for example, now, we have a particular problem that we are yet to solve, which is, should we ban ice cream in order for us to reduce the number of shark attacks? Because, there is a correlation, a spurious correlation. And we also, okay, should I start consuming a lot of chocolate for me to win Nobel Prize winner? The fact is just that there is a particular third variable lurking around that makes these correlations to seem that it is realistic, right? And most times, ice cream and shark attack, chocolate, and the Nobel Prize winner, we can say, okay, this is a spurious correlation, or correlation does not make it. It is very easy to mention. But imagine you have a lot of data in your organization and you want to solve a problem. And then you just find out this variable, and boom, let's try to work on this particular variable. So nevertheless, The major thing we are trying to discuss here is that the third variable that makes us to see that there is a positive correlation between ice cream sales and shark attack is that there is a particular locking variable called temperature. You know, during the hot weather, you know, people want to quench their thirst, you know, and they have to take a lot of ice cream. You know, ice cream is normally very cold. And then at that time, a lot of people, maybe they are closer to the river or they go to swimming pool just to, it is too much. Then they go to the river or anywhere and shark starts picking them up, you know. So it is not that ice cream has anything to do with shark attack, but just because of the hot weather temperature, we are seeing that these two things are what are related, right? And if we are not able to detect or to reason using our dark, right, we can't be able to what to be able to solve that problem. Or for the likes of chocolate consumptions and Nobel Prize winner, the third locking variable, which is the confounder here, you can see that this particular graph looks like the Fox structure, right? So it's really like the Fox structure. Then, like countries with high GDP, they are the one that's, you know, just because they are rich, you know, they buy chocolate, they consume a lot of chocolates. And at the same time, they are liable to win Nobel Prize winner. Maybe, you know, because they are rich, the way, the environment they are living in, if they want to do any research, they are going to have a lot of money pumped to it. No, they try to expect themselves the better, you know. There's nothing like electricity is going and stuff like that. They have money to get necessary resources for them to implement the research they are trying to do. And that is the reason why they're able to win Nobel Prize. We can see here that if we are not able to understand the concepts of the dark structure, like the major structure of the dark, which is the engine, we are not going to be able to solve that particular problem. The only thing we can say is that if someone asks you that ice cream is correlated with shark attack, you say, spurious correlation. The correlation does not make causation. But if someone asks, okay, how can you solve this particular problem without understanding directed acyclic graph or causal inference, you are not going to be able to solve it. Now, let's try to look at one or two examples for mediator and collider too. You know, now, if you are working in the marketing domain, and most times when you try to see a particular ad, right? Ad is like, if you want to sell your business now, you are going to have ads, maybe digital ads or out of home ads. Then you see people searching, right? It is the ads that the mediating factor. You see people searching, and at the later on they convert, they make sales. But the thing is that between ads and sales, there is a particular mediator, which is what brand search, right? You know, from ads, you try to search that particular brand and you try to make your sales. So most times when you are trying to find your impact of your ads on sales, so you have to make sure that the brand search that you have, brand search, is it something is going to be a mediating variable for you. And the last one, the collider, is that sometimes for someone to be a loyal customer, right, it depends on the sales they are making in your organization or your company, each time they come to buy from you, and the discounts, right? So you give discount to your loyal customers. But in one way or the other, discount and sales, they are not related, right? Discount is basically something, and so though you are trying to say, okay, you want to give discounts for people to make sales, but in terms of loyal customers, one comes after the other, right? So you already know people that make sales, you see that in loyal customer, then you want to give them what? Discounts. Now, I'm very sure before we leave this particular the directed acyclic graph, there is something called symptom paradox. Like when we are trying to look about correlation is not causation, this is one of the major paradox around correlation is not causation, why some people are trying to solve that particular problem. If you ask me, we have these notions, the bad, good trap. You get the bad, good trap. Let's say as a doctor now, you want to reduce the rate of heart attack. And when you are trying, maybe as an analyst, you find out that the data that you have, when you try to group by male, group by female, the gender, you observe that the drug is bad for male, it's bad for female, but overall effects of that drug, it seems to be possible. If you may ask me, okay, how realistic is that? For a drug to be bad for a male, but overall it is a good drug. Something is happening, right? It's a paradox there. Now, we have to look beyond looking beyond our data. In machine learning, we are very conversant. Okay, once I just have my data, did I understand the features? Then let me do my baseline model and let me start firing on them. Like pick from XGBoost to CatBoost to deep learning models, back to linear regression, back to random forest. A lot of machine learning models, and sometimes we even pick some features, just like, let me just say feature A plus B plus Z divided by 2, and let me see if it's going to improve my model, right? So we are very conversant with that in machine learning domain a lot. But the thing is that we have to look beyond our data. So in order for us to find the reality of why something might be bad for female, bad for male, and good overall. Now let's look at the maths. This is a very simple maths. When you look at this particular maths, you observe that for the female that does not take drug, right? And for the male that does not take drug, and for both of the gender that take the drug, we observe that the risks are higher, right? The female risk, like I said, bad, good, right? So the drug is bad when you take it, right? For people that take it, and we can see that when they do not take drug, okay, let me just there is a good effect for the people that do not take the drug than people that take the drug in terms of their heart attack, right? And we are seeing that, okay, fine, for female, the risk for people that take the drug is worse. For male, the risk is worse. But when we look at the total risk, right, the overall risk, we observe that, okay, people that take the drugs is better, right? So when we do the calculation, we can see that. But the reality is just that when we are trying to determine an effect of a drug on heart attack, we have to have our own, let me say, our own expertise, our own domain knowledge, the realities, right? We know that most times men are more prone to heart attack than female, and most times female take more care of their health more than the male. We normally try to, we have this high dosage consumption for risk, right, than the female gender, right? So if you are not able to encode this data generating process, you are still going to be taking a lot of time, finding a lot of ways to solve that problem. A drug bad for the female, bad for the male. When you try to look at them individually, then overall it is a good effect. But in reality, when you try to solve the problem, that that gender is a what? Is a confounder. Like, if you look at the structure here, it is similar to the structure we have in our Fox structure. So another example for that structure is confounding variable. We call it confounding variable, the third variable talking about. Then the gender, they are able to affect both drug uptake and high risk. And we observe that the overall result basically is that the drug has no good effect, right? It has negative impacts overall. So let's move to another one of simple paradox. Sometimes, if I may ask, when you look at this overall results here, the higher you exercise, the higher cholesterol level, and which we know that if you are doing a lot of exercise, you are trying to reduce your cholesterol. But in our data, if we do not stratify it by age, which is what the confounding variable here, we cannot able to get the actual what correlation. We expect that when you are trying to look at cholesterol and exercise, the correlation should be a negative correlation. It should not be a positive correlation, because you can't say higher exercise cause higher cholesterol level. But when you try to address it, when you try to take the consideration of the confounding variables, then you are able to measure the reality that happens. Well, you can see here that by age, the people that are by age, they try to they try to take their health more serious and stuff like that. But the reality is just that when you do a lot of exercise, right, your cholesterol level to watch expected to reduce. So if you have a negative correlation there. So data generating process, through that really matters. You have to make sure that reality first, like it helps you to put reality into consideration before you start doing your analysis or anything. You have better interpretations, you understand what data behave the way it does, not just what happened, unlike trying to do predictive modeling. Like, you also understand variables, your co-founders, because without that, you can't know your co-founders, mediators, or colliders correctly. And it's helpful to avoid paradoxes like Simpson. We also have Beck's and collider bias, but that can lead to false conclusion. Or like when you look at the bad, good, which is bad in reality, when you look at the cholesterol level and exercise. So rules for control, there are rules for this. I think these are one of the things where people actually stay away from causal inference, but the fact is just that for everything, there are some assumptions, so there are some rules that attach to it. When you have a co-founder, you must always try to control for it, right? The time did not permit us to do, but just make sure that you understand that. Collider, don't control for collider. We also call it immoralities. Like, imagine two different people that they are not, even let me say they are not married and they give birth to a child. Like, we call it immoralities. Like, they call it immorality in some. Mediator, the base rule is that you should not control for it, but at some point you might control for your mediator. So we also have a particular discussion alone on mediation analysis. Like, it's common in people that do structural equation modeling, statistics, and all stuff like that. But it's a more like advanced topic. So if you want to build that, the first thing about that is that domain expertise. Domain expertise can cut across your experience. Domain expertise can cut across you trying to talk to the right person that understand that particular domain, right? So in order for you to have your causal links, and we also have causal discovery methods. So we try to, everything that can be done manually, people can try to find some automation techniques for it, and causal discovery does that for us. Though it has its own limitations, and the fact that we are even machine is doing something for us, we also need humans to also look at. But this helps you to question, it helps you to question more the domain expertise that someone got it for you, or try to check one or two things through the automation method. And we also have the hybrid method, which I think is the best for you to build your data. You have the expertise, and then especially when you have a lot of variables, your expertise, and you trying to use causal discovery method can help you to simplify that particular data generating or with that process. So the first thing here now is the methodologies. We have our methodology in causal inference. Basically, two types of ways to do causal inference. Two major types: randomized control trials and then observational data. Randomized control trial basically is the gold standard for establishing causal relationship. And if I'm going to explain about what randomized control trial is, just that, okay, fine. Let's say I want to find the effect of drug on heart attack, right? And I have some people, I try to use coin. Okay, if it's head, I give you. If it's tail, I do not give you, and stuff like that. This helps us to avoid anything that comes with confounding variable or collider or mediating variable, because we are in control of that particular experiment. So after we've perform our experiment, we can just do normal computation and see the effect of our experiments. But the second method is observational data. Most times observational data is just the data you pick from your cargo, right? You are not the one that collected that data. Yeah, maybe I'm not even, you don't even have any domain expert in that data. But if you are doing machine learning, you can take that data. Once you know your target variable and other variable, you can build the model and say we have 90% accuracy, right? So observational data, you have to take into consideration some stuffs, like you have to really make sure that you achieve a particular purpose. Now, we have the fundamental problem of causal inference, right? The fundamental problem is that we can't observe two things at a time. Like, if I want to measure the differences, you know, I'm saying here, okay, fine, you want to conduct a particular experiment. We have a treatment group that take the drug, a control group that do not take the drug, right? But the reality is that for a particular person, at that particular point in time, you can't give them drug, and at that time, you say that they are not taking that drug for that particular outcome at that particular time. It's not possible, right? So that is one of the major limitations, but it's something that can be solved from observational data. Now, we have to understand that the fact that it's been mentioned that randomized control trials, and this is very common, the application of randomized control trials is very common in people doing, people in product analysis sometimes. You know, let's say it's very easy, and I don't think there's any ethical issues around it. You have a app, and then you try to randomize your customers or your users on your app. You show them this. Maybe you take your, maybe you try to do some modification before you release it, right? You show them the other one, you not show them anything, and over some period of time, maybe 2 months or 3 months, you observe maybe their conversion or how much they stay on your platform, right? Based on the thing. If you see that, okay, fine, that's trying to have that particular new maybe new design X people to stay more on your apps, then you can stay, okay, fine, for you are going to make changes to everyone to be using that particular new changes. But if you found out that it's not work, you'll say, okay, no, that one, there's no ethical issue attached. But in the likes of some of the limitation of random is ethical issues. You know, I can't say I want to study the effect of smoking on cancer and say, okay, fine, you come and I'll give you secret to be smoking. You know, I'll give this one. I will not give this one. So it's not possible. Or you try to say you want to study some other effect that relates to that, something that can cause harm to people, right? And it's expensive. It's expensive. You have to, you know, even if you want to do experiment, it's very expensive and time consuming. You know, follow up to that, because you are making sure that every problem that may arise when you want to do your analysis is being solved when you are collecting that particular data through a randomized control trials method. Now, for observational data, which is what a lot of companies do, which is what a lot of organizations are expected to do, and which is a very common data that we all have access to, you have to take some assumptions into consideration. I'll just mention them. Unconfoundedness, like I said, confounding variable causes spurious correlation. We must always make sure we account for it. And the variability, this one is just like unconfounded, but you are make sure that you capture all data generating process. You are able to know which variable is the confounder, which one is the mediating variable, which one is the collider, so that when you want to perform your analysis or you want to measure the impact on the study you are trying to do, you know that you are trying to what? You are doing the right thing. Positive assumptions, right? We call it overlapping. It's just like if I want to measure the impact of A on outcome Y, right? I must make sure that each of the outcome, they overlap, right? Let's say I have 0, 1, 0, 1. I will make sure that when I try to do my 2x2 matrix, we have for each of 0, 0, we have some population, 0, we have some population, 1, 1, we have population, 1, 0, we have population. Just make sure that there's overlapping between those variables. We don't want redundancy, whereby some variable will just be, you can't find them in positive assumptions. And we also have SUTVA, stable unit treatment value assumption. It's just that if, let's say you want to, let's say, I have a friend that's using a particular app, and you make sure that you give in that app, I was able to see the new design, but did not see, but when I was able to say it's affecting the user rate of my other guy, my friend. So it makes sure that there is stability. After the treatment of one unit does not affect the other. That's super. So we have just take note of these notable terms: individual treatment effect, which is not possible, but in simulation scenario you can do it. Like I mentioned, the fundamental problem of causal inference is that you can't measure two things at a time. Right? We have average treatment effects, which is something very common. We have the people that we give the drugs to, we have people who don't give the drugs to, and then want to measure the difference. We have average treatment effect on the treated. Sometimes we really want to see the impact of what we did on people that on the segment that we really want to address. We also have condition average treatment effect. This one is useful in the likes of policy intervention and stuff like that. We also have local average treatment effect. These are some notable terms that we should just understand. So these are some of the tools that we can use to do causal inference of general. I think we are all familiar with ordinary square methods. So Facebook also has the Python library called DoWhy. This is also automation way for you to handle it. Causal Pi. This is based on Bayesian causal. WMN. This everything that we have here is open source. DoWhy, Causal Pi, WMN, open source package. And ordinary square method. I think we all know we can all use regression, right? So common mistakes that people make in is that for randomized control trials, like it's been mentioned, it's a gold standard, but it is not the sleeper bullet for every causal questions. Omitted variable bias, this one we face it a lot in observational data, right? Imagine there are some variables that you cannot measure. You cannot measure, let's say someone is using your website, right? You cannot measure their intent, right? But you can measure some other thing. You cannot measure my intent on your app. Maybe the reason why, let's say you have a platform that, okay, you have someone to upload their data for them to use your Power BI analysis, right? The outcome is that you want to see the usage of the customers. Why the intervention is that, okay, fine, upload your data. Maybe the reason why you see some people uploading is their intent, right? To be able to perform analysis, but you don't know my intent, right? So those are some very bad I can do. Not consulting experts, just pick the data, you go and you say you want to do that, or you are trying to use causal discovery method blindly. Machine learning techniques or metrics, trying to think that maybe when doing your analysis on observational data, you are trying to judge the performance of your the impact or your estimate on R squared method and stuff like that. So we also have our machine learning techniques. You can't say you want to use deep learning methods to solve this problem. And sensitivity analysis, a lot of people, when you're trying to conduct your causal inference method, they don't perform sensitivity analysis. So basically, this sensitivity analysis is a way for you to confirm that the estimate you are trying to do is something that is that has passed some test, right? So let's move to application of causal inference. I think this is the end of our agenda, and we are running out of time. So basically, the part is just that I've seen that some people have said, okay, this is the first time hearing about causal inference. The idea is just that some of the apps that we use on day-to-day analysis, they have a they have a particular thing, right? A particular thing that does causal inference. That's all what they do to measure some impacts. For example, like I said, in marketing, medicine, they use it. Pricing might not know, but Amazon use causal inference. Especially, we're all familiar with Spotify and Netflix. I think they are one of the major frontrunners in causal inference research. So they have a specific team that does causal inference for them. Like they do causal inference in this Spotify and Netflix. When you go online, you see them having papers and travel, booking.com, Uber, and some banks and banking, they also use causal inference. But I think most of these companies I mentioned here, they are in the Europe part of the world, European part of the world. Mostly they implement a lot of it. But if you go to YouTube online, you see these companies trying to implement causal inference to solve a lot of interesting problems. Like if I may mention one of the interesting problems that causal inference is being solved is basically when the likes of Uber are trying to make some intervention on their pricing, right? So in pricing, they are trying to find if we increase the price here and reduce the price here, what is the impact of reducing the price and stuff like that. Now let's move to the business scenario that we are going to discuss here. This one is going to carry everyone along, whether you're a data analyst and stuff like that, and you want to solve a particular business problem. So the content is that you are working in a startup and you want to increase your sales from existing customers by encouraging them to buy one or more to your discount incentive, right? So the goal is that you want to measure the effect of the discounts on customer behavior and ensure a positive return on investment. You can't say you want to give discounts just to have negative impact on your business. It does not work like that. And then the other is that you want to avoid wasting money on low value users, right? And the discount is designed to be profitable only if it generates greater than $1 incremental sales, right? The question: how can you measure the effect of the discount and make sure our experience is positive ROI? We have our variables, like I mentioned, you have our data visits, number of visits to the website during the test windows. We have discounts, whether the customer receives discount or not. We have whether the customer is loyal according to the information above. Total sales recorded. Now, a data analyst will do, sorry, a data analyst will, okay, fine, let me do univariate analysis. Our sales is our outcome, right? And we want to see, we call something like, let me say, the impact of the discount. People giving discount and not people giving discount. If you remember, in the second round of causal inference, we have intervention, right? Doing, right? So in your business, you already have the data that you give some people discount and not give some people discount. You already have your sales, right? But when you look at the overall populations, in here we are trying to measure the average treatment effect, right? Since I can't do individual treatment effect, I can do average treatment effects. Then a data analyst just go, okay, fine. Let me group by the discounts, the sales, the average sales they make, then the negative, the what people did not give them. And wow, you found out that $4.8 leaves. Oh, this discount is very beneficial. And then we are trying to tell your stakeholder that this is the impact of the discounts, trying to have 4.8, incremental impact. The data science feedback, what have you done? You just take two variables, discount and the analysis is too simple and lacks realism. Then our data scientists say, data science will love a lot of features, like especially with the machine learning model has 100 features, 500 features, just put everything together. Okay, instead of looking at discount alone, okay, let's go back to find the people without discount and are they loyal, and the people without discount that is not loyal. Let's look at them, and you found out that you have $12 lift. Wow, this is too high. So stakeholders will buy the idea, like just because of the discounts we are seeing $12 lift for our sales. Yeah. Then data science B looks like the two of you are trying analyst A, B. I think you don't really understand all this magic that random forest can do for us, right? You don't understand what this magic random forest can do for us. Then, it picks that particular data point. This discount is lower. Try to pay the sales, right? And in the long run, it's trying to measure the impact of, there are ways that you can interpret the model that you try to find the impact of discounts on our sales, That's why the fact that you control for visit and is lower, and you find 0.35. You ask the question, business should stop the discount because it's less than what? It's less than one incremental sales that we are planning to generate, right? Then, the fallacy is just like this. So the bias for data science B is that the data scientist thinks ML is a magic. You see this particular thing in my model, you want to include all variables, like to avoid confounding bias. Like you want to do unconfounding assumption, you put everything. Then, the fallacy, more data, better model, it causes it. Then you find out that selection bias is looking at you. During the point of trying to put more features into your model, you have tried to take what is not supposed to be in your model. You have control for what is supposed not to control for. And if you remember vividly, out of the three structure we have confounding, mediator, and we have collider. The process is the recommended solution is that if you want to solve that kind of problem most times. So though this example, okay, process, you have to understand your data generating process. You can't be a causal inference data science. You can't apply causal without understanding data generating process. Using that, you can't. You have to understand that. Then you have to do some adjustments. We can't really touch these statistical adjustments because of the time we have. Then this is the reality. When you look at visits. The fact that, when you see that some people used to come to your what very well, you tends to give them discount more, right? Then they tends to make more sales, right? Then when you think of it later, because you give someone discount and they do mail sales, you take them to be what your loyal customers, right? In the wrong of trying to solve that problem, that you do your machine learning magic, or someone trying to do data analysis magic, you don't account for visits. You are accounting for discounts and it's loyal. Someone is accounting for discount alone, right? And then our magician data scientist is accounting for every variables. The better the more the features, though the better the feature, but most times the more the features, the better the more trying to pull everything. Now, we've already included a collider that was going to affect the reality. Now, this data is simulated data, and then it is being done with one of the panel of causal inference. I think I have the link in this slide. I think it's Dr. Joan. He does causal inference and is trying to explain that scenario. The link is there for you to look at how causal inference can be able to solve a lot of business problems. The actual lift is $2, but you can only solve this problem when you control for the right variable, not for every variable. All right. Now recap. Just take notes. Correlation is not causation, but sometimes correlation is causation. Practical application, the first rung ladder application, I put LLM here, when you're trying to predict, the lives of large language models, they work on correlation. So you can't say just because we have causal inference, correlation is not useful. No. Your machine learning can still solve some business problem. Your deep learning still solve a lot of problems in the industry. So methodology difference. Causal inference is different from the traditional machine learning. So because causal inference, you are trying to use your mind before the data, right? Synergy, how do they work? They work together. We have causal ML techniques that works better. Sometimes when you have a lot of features in observational data, causal ML can help to do some magic, right? When you want to do propensity score, when you want to try to reduce the variable to, I think there are something that it has to be more practical, like depth than as done practical. Business context. Most business questions are causal in reality. What if you may ask me now, if you are working in a churn organization and they ask you to predict customer churn, then after predictions, what next? Right? The reality is that what next is that what you may actually do is that, let me just put this scenario. If you are able to understand why they are leaving, right? It helps you to avoid what's next in the wrong way, right? Why are they leaving? Why are they leaving? It's more important that they are leaving, right? If they are leaving and you think, okay, fine, let's implement this, let's do this particular intervention for every customer that our model apply their leave, let's still send them $1 names. And you say that, okay, there's maybe your period that 100 people are leaving your organization, and you use $1 to send that message to that 100 people. That's $100. And you later find out that the retention rate you can able to recover is just 10 out of 100 people. So you use $100 to see out of your $100, $10 is it's only $10 that is efficient, right? But imagine that you know why they are leaving. Out of that 100 people, you already called as this. I think these some people they are what they are not going to comply, right? They are not going to be compliant. Some people you don't even need to wake them up. The only people you need in that category of business is that the persuaded one. Which customers are the one that if I send this mail to, they will come back. You are not going to leave. So imagine out of the 100, you are just 30 people, and you send, even automatically you are able to reduce the amounts your CFO, your chief financial officer will spend, or the finance account will spend to allocate for the 100 customers to like $30. At least that is the game for the business, because from every business, everything, maybe they go back forth, they do this, everything still boils down to what? Profit making, right? So the last one is more to learn. Like all these things, they are practical measures. It's very, very practical. Very, very practical. And this is being used in a lot of domains, medicine, banking, like I mentioned earlier. So these are some of the things. And resources. So the first book that I will ask people to read is this book, The Book of Five by Judah Bear. Is the one that actually Because I really love when I read the book. You learn a lot from him. I think it's more it's above 80 years, but when you see him speaking, you really enjoy him a lot. And then I actually don't want to put order because there are a lot of resources for causal inference, a lot. So this LinkedIn post, when you go there, the poster mentioned 5, but when you check the comments, you are going to see more than 20 books on causal inference. That's why I put the post notes. We have the book of why, we have the brief and truth, we have the mixtape session, we have the uh Python for causal inference by Matthew Sparker. We have the one from Alexander Mulak. We have a lot of books that really talks about causal inference. And a podcast, if you check for Alexander Mulak too on YouTube, he has a podcast that he has interviewed a lot of people implementing, solving problems from booking.com, Spotify, even a lot of organizations that they are trying to use causal inference to solve problems. So this is the end of the session. And do you have any question? Thank you.
Yeah, thank you very much, Nasruddin. Yeah, we have a couple of questions. Let me just open the chat.
Yes.
Yeah, so the first question that we have is, so causal inference is used for recommendations.
So it is causal, not casual.
Oh,
Causal
like
inference.
why do I keep
Causal
on
inference.
saying causal? I've learned.
Yes.
I meant to unlearn.
Yeah.
Oh,
Causal
goodness.
inference. Causal inference. Right. So basically, recommendation from what I've read so far, recommendation engine is more is one of the applications that predictive pattern recognition is still well recognized and in consulting as it stands for now. So using the normal way of our recognition engine, maybe a collaborative method and some other methods is still one of the best way to do recommendation engine. It's just like we are trying to learn it. Most times you are trying to learn a pattern recognitions, right? Because this one like this, right? Then can we show you to this kind of person or this particular country? They are trying to watch this particular video. Then let us release more to the people in this particular country. So for recommendation, I think machine learning methods and other familiar methods before causal inference is still well applicable from as it stands for now from what I've read so far.
Okay, thank you very much. Then the next question is, can you recommend resources to get a hands-on practical training on causal inference? Are we also getting the meeting recording? Yes, you get the meeting recording when it drops. So yeah, you can answer the first question.
Yeah, the first question is that if you go to DoI, it's an open source by Facebook. When you look at their documentation, you are going to see a lot of things on causal inference. DoI library, you are going to see. And there is a particular book that The Brave and Truth by Matthias Farquhar. It is open source. Very, very solid book for causal. Very, very solid book for causal inference. And if you go to YouTube too, just look for causal inference, you see a lot of resources on this. So there are a lot of resources, but if you want to get started or you want to fall in love with causal inference, when you look at the DoI documentation, you at least it will help you a lot. And then you can also look at Alexander Molak YouTube podcast. Then you are going to see a lot of people doing causal inference applying it in a real world situation.
Okay, thank you. Next question says, thank you very much, Mr. Rahim. This session is wonderful. Thank you. I'd like to ask, how can one learn more and build a career in this field of causal inference? For context, I'm a data scientist and I've also had some years of experience working as a biostatistician for clinical researchers, but I'd love to learn more.
Yes. So for causal inference, mostly, I think to be honest, in our locality in Nigeria, we don't really have much people into it. So if you are able to look at this link here, like when you look at this link here, there are a lot of people that you can follow on LinkedIn that they talk day to day about causal inference. They apply it, they talk it about. Once you start following them, the algorithm will start bringing them, a lot of them to you, then you start learning. And the thing you can also do is that like I mentioned, you can, I think the book of why by Judah Pay, when you search online, you can see, or you can buy on Amazon. Then when you start reading on it, you start learning one or two things about causal inference. And then The Brave and Truth by Matthews Farquhar, right? It is a very, very good resource. Unless I forget, there is a particular, is it MIT course on causal inference by Susan Atti. You can find it on your YouTube. Susan Atti, causal inference. It talks like from like 12 series of lectures on it. So it is a very good resource that you can start to get introduced to causal inference.
Okay. Another one says, how important is importance of feature engineering in causal inference?
Yeah. So basically, when we are talking about feature selection, feature importance, most time in machine learning, feature importance is after we've done everything, after you build your model, after you've done everything, then you look at, fine, what can I do? Then you try to look at your feature importance, okay, to see the top ranking features, maybe, yeah. But the thing is that in machine learning, like I said, most times they are correlational based, they are pattern recognitions. They don't care about whether something is spurious, it's not realistic. Once data just see that, okay, this move with this, right? It's the models keep on enjoying and gives you that wonderful model performance that you want. But in causal inference, it's not like that. Your feature importance, you can't say you have feature importance, but what you have is better than feature importance, because before you even start implementing causal inference to solve a problem, you have already put your mind before data, right? You know which variable to account for, right? That we make sure that the effects of drug on heart attack is not based on spurious correlations, because you have to account for the confounding variables, right? You already know that if you put this variable it will cause another collider bias, right? You have already tried to use your DAC to explain everything. Then you know that when you are trying to find the impact of your treatment, I've not even talked in causal term, we call it treatment and outcome. You want to find the impact of treatment or outcome, the impact of drug on heart attack, the impact of discount on sales. Then you know that I could find the lift that you are trying to have, or the impact you are trying to have is realistic, and you can discuss it with your stakeholder. So basically, and in terms of feature selection, in machine learning, most times we normally try to, in statistics, we have this the way that we normally apply. Sometimes you start from small features, sometimes you start from that feature, you start dropping them. In causal inference, everything boils down to the engine. Make sure you have a directed acyclic graph, DAG, your data generating process, before you start any of that thing.
All right. Thank you. Also, another question is, can we get the name of the book in the chat? So I think some questions like that. So some people asked if they can get those things that you mentioned in the chat. Then the last question that we have here is, how long will it take a data scientist to fully gain working experience of causal inference to apply it in other sectors?
Yeah, the reality is just that if we look deeply into maybe you are working in data science, as a data science in a particular domain, right? If you look deeply into that, some data process where you have done before, you found out that you can apply causal inference to make it more realistic. Most times the dilemma data science have is that after we build our fancy machine learning models, right? How do we even interpret? Like, how do we even try to talk to stakeholders? What are the revenues, or what are the impact, the return on investment that this will bring to us? If you try to think causal in a causal inference perspective, right? You are going to have this, it's going to improve your confidence as a data scientist working in organizations. You know that what you are trying to do is something that will be beneficial for the business. So imagine now that I am working in a telecommunication company. These are one of the applications of causal inference. And over the years, we've done a lot of campaigns, right? You know, all these campus bumper campaigns and stuff like that. And you know, for every business interventions that you are trying to do in your organization, you have an outcome for it. And maybe you are trying to measure conversion is the outcome of maybe when you change your user interface, you know, conversion is the outcome. Or you are trying to do a particular ads and you have your sales as your conversions. You are trying to reduce the price of your business. You are trying to increase the number of units sold and stuff like that. When you look at everything like this, and the thing is just that you are not trying to be more realistic with the problem you are because causal inference is you are asking the right question at the right time. So now I want to do the impact of this particular campaigns on our maybe popularity of our telecom industry. Then you pick the data, you have your DAG, you know the right adjust, you take care of the assumptions, you talk to the stakeholders, you know, the domain expert, you have the right adjustment techniques to do it. It's because time does not, I can't fit everything to this particular session. There are some things that we also have to understand. Like we have something we call backdoor criterion. What does it mean is that you are trying to avoid backdoor criterion, you link it back to what we call confounding bias, right? Like unconfoundedness is something, it is very, very key for that. Once you can do that, then you can measure the impact of your interventions on your outcomes. Then you can able to be realistic and tell the fine, this particular campaign that we did or so like this, it is what it is, it has this also impact. It has positive or negative impact. But if you are trying to use data science to solve some problems, you know, your X and Y alone might not be the right way to frame that particular problem. So in a nutshell, most times, some questions that business want to solve, it is through, they can only solve it very well through causal inference, using causal inference techniques, or else they'll be flying around. Like, and if I may understand, you know, causal inference also helps us to think very well as a data analyst. If you are a data analyst that you know causal inference, the way you analyze data will be different because you want to put your minds, and you're not putting your mind alone, so that you are encoding that your mind, you are saying it like this, like, okay, fine, this variable, then you know what may cause spurious correlation. Like I said, if you are doing anything that relates to statistics and machine learning, you are just under correlation association. Yeah, everything you are doing is based on association. But when you want to intervene, you know, I want to change this, and what is the impact of this? You know, in business, maybe we are selling something $100 before. If you change it to $90, after what is the impact of changing it to $90? Those are the questions you want to ask. I have these customers. Why are they leaving? Right? I have this customer. Okay, which customer are they persuaded on? What is going to be the impact of that? I have this. We have these new drugs. What is the impact of new drugs? No, you are going to give some people the drugs. I don't know. You are going to make sure that the family does not take the drug first. Then you are going to measure the incrementality impact of that stuff. And then at that particular point in time, you are solving, when you ask the right questions, you are using the right tools to solve that particular questions in your business. So you don't need, and if you want to, if you're a data scientist, 3 to 6 months, depending on how much time you spent, at least you'll be able to get where to understand one or two things and be able to apply causal inference to solve some business problem.
Okay, thank you very much. I think that would be all. Then the one that I was meant to read, for the person that joined late, yeah, you getting the slides and the recording too. So yes, the slides, the recording would be available. For any more questions, we can't take any more questions because of our time. If you have any more questions, you can reach out to the speaker. I'm sure if you followed us or if you check our promotions, you would see him there, and he's also displaying how you can reach out to him, which is fine. So yes, thank you very much for your time. And yeah, I think that's mostly it. So I'll just be taking the remaining I'll be taking the remaining parts of the call, so we can call it a day. So yes, please follow us for more updates as time goes on. Yeah, how we can join Machine Learning Lagos, I'll be adding that. Then we have our April office hours, and would like everyone to come for our office hours. It's something like this, but it's a Google developer expert or Googlers, and it's basically on YouTube. So it's going to be on YouTube. You'll be able to will be streaming it, and you can ask any questions on it. So please and please register and come. We'll still be making some more promotion on that. I just dropped the link for you to register. Then and also our Make Technical session is also coming up. Like our technical session is monthly. Then for people that want to join our community, you can join us with the link I just shared. We'd also like your feedback, please, and please. It's your feedback that keeps us running and knowing what we can do better. Is it that you want us to bring somebody, or there's something that we're doing in a session that is not fine? Please, just go to this link. I'll drop the link soon. So please just go to this link and drop your feedback. It's like a 1 minute thing, right? I'm trying to type out the link because I didn't even copy it. I'm almost there. Okay, yes, that should work. And yes, thank you very much, everyone, for coming, for staying to this point. The recording will be up. The recording will be shared. If you registered on the community, you would see the email, and we'll also share it on our public platforms too. So see you in our office hours and in our remaining sessions. Yeah, I'd like to see everyone actually. Thank you very much, and please don't call it casual. Like I've been saying, casual is causal. Let's pick that one soon. So yeah, bye everyone.